So for the remaining maybe 2 hours of our course, I would like to do a little bit of on the topic of applications of tunneling. Tunneling is a quantum effect. Well, basically it's a wave phenomena. So it is very appropriate to have a discussion on the topic. As I said, the cutoff point is at the end of the last module on the physics of molecule for exam purposes. So this extra module on tunneling will be excluded from the final exam. In addition, please note that problem set 6 was issued on Sunday, and it is still the coming Sunday. For this part, I will take a more leisure mode, meaning that I will do it like a seminar mode. So some of the details I may not go into them in the discussion. But I checked that from your notes on quantum mechanics 1, you have some part on the tunneling part, although I'm not sure what it means. Sometimes it was labeled optional. So did you do tunneling, those sections in Professor Liu's notes? Did you do that in the last term? Okay, so even it says optional in the notes, so you know that, right? Okay, good. Okay, good. Let's start. I will start the discussion with one important motivation that has to do with nuclear physics. Okay, so we have done atom molecules, so I intentionally just want to go away from atoms and molecules, and then therefore I selected a problem related to tunneling in nuclear physics. It is alpha particle decay. So in 1122, which is your year 1 second term course, Dr. Lin has this topic in his class notes. I had those chapters. Okay, so at least you have some idea what is a nucleus, right? A nucleus consists of some tens, usually maybe 50 of nucleons. They are protons plus neutrons. They are collectively called nucleons. They interact through nuclear force. Nuclear force are short range, and the nucleus is very dense. So basically, you can think about it as densely packed with nucleons inside the nucleus. The size of the nucleus is of the order of 10 to the -14 to -15 meter. 10 to the -15 meter is called femtometer, or more related to nuclear physics is called 1 Fermi. Well, FM, so double meaning. Okay, so Fermi is the famous physicist who did a lot of experiments by flying neutrons into many different nuclei, and he got the Nobel Prize for that. So that is easy to remember. 1 Fermi is about the size of small nuclei. 10 Fermi is about the size of big nuclei. And what is the alpha particle? Alpha particle is a helium nucleus. So it has 2 proton, 2 neutron, something like that in a cartoon way. So you may think occasionally there is something like a temporarily helium nucleus existing in a bigger nuclei, and then can it suddenly get out? If it does, then you have an alpha particle decay. Okay? Facts. Alpha particle decays exist. we can use a counter to measure them, okay? And then the question becomes why? Well, the probabilistic nature has a lot of similar character to our spontaneous emission discussion in atoms and molecules as well, okay? So we have a nucleus, and then you wait for a while, you don't know when, then suddenly there's an alpha particle comes out, okay? So if you have a collection of such nuclei, then how many of them will decay? It will depend on how many possible nuclei that you have, and then it is a dn dt equals a minus rate times m. So similarly for spontaneous emission, we have this is related to the lifetime, okay? And we did the, for example, 2p of hydrogen, what is the lifetime? Okay, we have some exercise for you, sample question for you, okay? So similarly, this is also 1 over it is a lifetime of the nucleus. So we have the same thing, lifetime against alpha decay. With this background, let's look at some numbers, some data. So here are a few nuclei that can undergo alpha particle decay, and look at the lifetime. They vary hugely. Now, not very often in physics, you have one physical quantity that can span that many decades. You see? It started from less than a second to the age of the universe, right? 13.7 billion years, that's about it, okay? So now you see, lifetime of alpha particle decay from various nucleus could span that many orders of magnitudes. Another occasion, let me tell you, is conductivity, right? So you have something that is not conducting, insulator, that has a very small conductivity, all the way to you have superconductivity that goes to infinity. All right. So, but really in physics, not many quantities show this wide range of numbers. But more than that, look at the outcoming alpha particle kinetic energy. In nuclear physics, the energy range is MeV, 10 a million, 10 to the 6 eV. Now look at this number. It is just from 4 eV to about 10 eV. No, 4 MeV to 10 MeV, right? So the outcoming alpha particle vary in kinetic energy, but not by much. However, you see that the lifetime vary by a lot, okay? And then you also see a little bit of correlation. When the alpha particle comes out with a higher kinetic energy, usually that nucleus has a shorter lifetime. But only half of the kinetic energy, 9.5 divided by 2 is about, 5, okay? So 4, this is about only 50%. And then it is off by many orders of magnitude, right? Okay, so that is the picture to keep in mind. That is the problem that we want to discuss through the idea of tunneling. So in nuclear physics, for alpha particle decay, we have this idea in mind. If the alpha particle can come out, so it is a helium nucleus, it has +2 electron charge, the daughter nuclei, meaning the remaining nucleus, will have 2 positive charge less. So it has Z-2 atomic number. It has this Z-2e positive charge remaining in the nucleus. So imagine the potential energy between this positive charge and the other positive charge. It will give us a Coulombic. So this is Coulomb, right? Something like that, okay? So there will be a positive part in the energy as a function of the separation. This is the separation, okay? But now, inside the nucleus, there's strong nuclear force. The other nucleon do not want the alpha particle to go out, is pulling it back, so it is trapped inside the nucleus. So thereby there is some nuclear force potential energy well that comes from the nuclear attractive force. So putting the two things together, a Coulombic tail, and then you have some trapping due to nuclear force. We have this characteristic profile, okay? So now we know the kinetic energy of alpha particle that comes out is typically of 5, 6 MeV. So according to the number, this alpha particle energies is about here, okay? So it's not sufficient to go over the barrier, but yet it comes out, okay? So that is the puzzle in the early days of quantum mechanics. So to summarize the situation, we have this kind of problem in hand. So we have an alpha particle trapped inside the nucleus. Occasionally, somehow it can appear on this side, but certainly it has insufficient energy to go above the barrier to come out. And at the end, it was tunneling that explained the phenomena. And then with this idea, we could also start to consider fusion. Fusion is the other way around, right? So if I have a helium nucleus going inward into the nucleus, this is repelling it. It doesn't want it to go into it, okay? Nonetheless, this extra nucleus could combine with the bigger nucleus and then form an even bigger nucleus that is called fusion. 2 nuclei combined, okay? So once this alpha particle decay question is understood, we have a lot more possibilities. So in order to understand tunneling, then we need some more background. I checked that you have this background last term. So in the following pages, I just want to remind you of some idea that you learned in Quantum Mechanics 1 from Professor Liu. 2 ideas are valid here. One is traveling waves, because in our atomic and molecular physics module, we discuss most of the time stationary states, solution to the time-independent Schrödinger equation. What are the allowed energies? All right. Now you will see, you have seen a lot of standing wave solutions. But for standing wave solution, there's an embarrassing part. The wave doesn't travel it's not moving, and then how could it penetrate something? How could it tunnel through something? Okay, and then we need another idea called traveling waves, and then we have continuity equation, and then you have the J operator, the current density formula. So I hope this part is mostly a reminder for you. So first thing first, we need something traveling. But as you will see, after we know how to write down something traveling, then there is an issue comes out, how to normalize them. Okay, and that is I just want to mention that problem, but we don't need to solve that problem in order to move on. Why do we want to have something that travels? Because we want to have this picture. The alpha particle going in, try to hit the barrier, see whether there's a chance to come out on this other side. Okay, if it does, then nice, there will be alpha particle decay. Okay, so traveling thing, well, not difficult to write down. So free particle, this is the dispersion relation, p squared over 2m basically, right? And now you have plane waves. You learn a lot of this from courses in classical mechanics and also in electromagnetism. So with this EIKX, that's the spatial part, and then you know it has its own time evolving factor exponential minus I omega t. This omega actually goes with this k, right? So you can think about it as E divided by H is an omega, right? So it has to do with k, it's related to k. It is called dispersion. That's why it's called dispersion, right? That is borrowed from optics or EM waves. And then you know that this is a traveling waves traveling in the positive x direction. And then with a E minus IKX, this is traveling to the left. So we know things that are traveling. Immediately, there's a technical issue. For example, if you have a space part like this, EIKX, how to normalize it? Okay, now this problem is not specific to EIKX. Basically, the problem arises because in this case, you have continuously allowed the energy. You give me any k, there's a E. That is to say, k is not discretized by any boundary conditions. Therefore, you have continuous k and continuous E. You learn a few ways out. I just want to remind you that. One way is to look very fancy. You invoked, let's normalize it by some delta function. This is Dirac delta, okay? So you want psi kx and psi k prime x integrate over all possible places is a Dirac delta, okay? Well, fine, that works. That is a very nice thing. I checked that you had that in your notes. And in my viewpoint, it amounts to solving this normalization issue by defining a new normalization method, right? So you change the normalization definition. Behind this scene, you have Fourier analysis, etc. There's another way to do tunneling problem, avoiding the normalization problem, is to superimpose many different values of k to form a wave packet. So you have a localized wave traveling towards the barrier, and then you start analyze things. This is a very nice way to do the tunneling problem but the mathematics is more complicated to follow. I think you can find such a discussion in the book by Shankar, Principles of Quantum Mechanics. A very nicely written book by a very good author. And then another way, if you go into solid state physics, you have this way to keep the normalization definition. Then you use a trick called box normalization to normalize the traveling wave. The idea is the following. Say 1D, you may think about it as a flat line in which the wave travels, right? But then you can do something like a periodic boundary condition, or you are thinking about a very long wire, okay? So think about it. You just keep on running on the surface of Earth. You may think you are running on a straight line, okay? But if everywhere is on land, maybe some years later, you will come back to the starting point, okay? And you thought you are running on a one-dimensional space, but actually you are moving around a big ring, okay? So that is the idea of box normalization, so-called. So you are using a finite big space to mimic an infinite space. This is also called periodic boundary condition, okay? And the nice thing about that, you make a long wire L in length, and then you put the two ends together, okay? So the wave could traveling, and then you have the idea of traveling to the right or traveling to the left. Actually, it's this way or that way, okay? Now, once you do this, you can normalize it as usual, and that is called box normalization. But behind the scene, K is again discretized. So all in all, I just want you to have this take-home message. We know how to write down something that travels, no problem. But once you have something that travels, you must pay some attention to the problem of how to normalize the traveling waves. Second point, you also have that in your previous course. There's a formula that you can calculate something called the current density. Of course, we don't have charge in the formula, therefore it is called probability current density. In electronic engineering books, you have the same formula. They will put a minus E charge in the formula. This is called the electron current density, quantum mechanical form. So again, I checked that you had that in your notes. The way to derive this form is to go through the exercise of this is the probability density. You do the two derivatives and then look for a formula of J such that you have the continuity equation, okay? And then after that, you found this, this is the current density formula. For our purpose, we are not very ambitious. We only need the 1D form of this formula. So the gradient of phi is d phi dx, but remember gradient is a vector. Formally, there is a unit vector associated with the direction. So here is a 1D version of the previous formula. Many will use this, but to make the point, I add in a unit vector just to make sure that you know this current density is a vector in principle. So now it's interesting to see, now we know how to write down something that travels. Behind the scene, actually, there's a time part, but plug in the formula, all this will cancel, okay? So that's why usually we only care about this. So you plug this into the J formula. Now you must do it once in your lifetime, okay? You will get this answer, okay? So therefore, next time when you see something like this, don't do it again. Automatically, then you know it is about the velocity. H bar k over m is the velocity. K is the wave vector, right? So h bar k is the momentum. So this is the velocity times a squared. That will be the J, okay? So the educational value is as follows. Don't do it again. You have done it, okay? So next time you see such a term, AEIKX, J is automatically the velocity h bar k over m, then this amplitude square. Okay? Now, this amplitude square is actually phi square. So it looks as if it is a probability density that is moving, and then give you the probability current density. That makes good sense, isn't it? Physical sense, right? Probability density moves with velocity v, give you the current density. Okay. Now, for those who know a little bit solid state physics or E&M, the electric current is minus the density of electron, the velocity. Okay. I think you may have it in your E&M course already. Okay. So it is basically at the analogy here. Okay. But it is good that it comes out from our formal quantum mechanical formula. So when you see this, don't do it again. It is traveling to the left. So the velocity is minus momentum divided by mass. So this, and then the probability density is moving with minus v. This is the current density. All right. So summary, when you see this, J is that. All right. Now, very interesting exercise. If you haven't done it up to this point, you must do it once and then take the answer. What if I have these two terms together? Now, some of you start worrying. There will be many cross terms. Come together, okay? That's true. You plug in here two terms, and then you have derivative two terms, multiply four terms, and so on. And then luckily you have a minus sign, okay? So believe it or not, the answer is simple. The intermediate steps looks complicated. Then the answer is just this, okay? So summary, next time when you see this, don't do it again, but you must do it once, okay? If you haven't done it once, you have no right to use the answer, okay? Now, you have these two terms, then the current density has two parts, contributed by right moving terms, velocity, probability density, plus I, direction. The second term in the opposite direction, minus I, same structure, all right? And that's why in doing typical tunneling problem, when you have on the left-hand side of the barrier, you have this wave function, then you are regarding it as two terms, meaning it is, well, every book draws this, it's an incoming term, there's a refracted term, okay? Now, the reason I believe is that the current density is contributed by moving to the right, that is this term, okay? And another one that is moving to the left, and this is coming from this term, okay? And I think this is why it is usually drawn like this. So summary, up to here, introduced how to write traveling things. Secondly, given a traveling to the right, what is the current density? Traveling to the left, what is the current density? Okay, now several exercises here, very interesting one, try to do it. We have been doing a lot of stationary states. So this is a stationary state, particle in a box ground state. In the past, we don't care about the time term, but now you want traveling things, right? You want time varying things. So let's put that back in. Now, plug this into the J formula and see what you get for the current density. Can anyone give me the answer immediately? Three seconds. Yamo, do you know the answer? Hello? Are you doing that? You don't need to do that. You will get 0. Now, the next thing, two stationary states of different energies. So as time evolves, the wave function will evolve like that, okay? Again, it's a very interesting exercise. Plug it into the formula for current density. Well, many terms, don't give up. At the end, the answer is very physical, okay? You will see how this, now you are forming a wave packet, although very simple one. Two terms, you will see how this wave packet moves in time. And even more interesting case is the following. My wave function has a magnitude, amplitude that is R dependent, as well as a phase that is R dependent, okay? So now you have two spatially dependent things, or in X, you have this and that, okay? Now, plug it into the formula for J. I mean this one, okay? In one dimension, you will have two places where you have X derivative to do. So you will do this, that will be easy. Then don't forget you have a phase dependence to do the derivative, okay? Now you will see whether a phase dependent, positional dependent phase will lead to something in the current density, okay? Now, try this, you will get a very interesting and compact answer. In your solid state physics course, if you go into that course, you will see this is related to the current in superconductors. So let's get back to your tunneling problem, a problem that you are familiar with. A standard setup is the following, although somehow misleading, I would say. So this is the standard problem. On the two sides, I have 0 potential energy. In the middle, I have a barrier, but it's just a one flat barrier, okay, U. I say it is slightly misleading because more generally, I think this will be a better problem to solve. Okay, so you have this 0, you have this U, you have this minus V, for example. Okay, that will be a more general problem to do. But now I hope that you will not be misled by this equal potential on the two sides of the barrier. Here, I remind you of the standard way to set up the problem. So you have the left-hand side, you have an incident part and a reflected part. I hope you know why now, okay? Because this current density is going into the barrier, this current density is leaving the barrier, moving backwards. And then on the right-hand side of region 3, you have a transmitted one. The reason is that this is plus IKX. The current density is moving towards the right, okay? And then in the middle, you have a finite region. Thereby, you just use the Schrödinger equation. You are interested in energy lower than the barrier. Thereby, you will have this exponential type of wave. One is dropping, one is growing, but it doesn't hurt. Even it's growing because it's of finite width, okay? Then you match boundary conditions. The wave function is continuous. The slope is continuous on the two barriers. You have 4 boundary conditions. You have 5 coefficients, but one of them can be arbitrarily chosen. Thereby, you have sufficient condition to fix the remaining 4 coefficients. The quantities that we are interested in are the reflection coefficient, capital R. At this time, we have a good definition for this thing. It is the reflected current density upon the incident current density, okay? That's why we need the definition of the current density. And I must say that this definition is the general definition of the reflection coefficient, okay? Now, many of you learned this problem. If you learn it incorrectly, you will think the reflection coefficient is B divided by A, okay? Now, it turns out to be right, but it is not the proper definition. It is about the current density, actually. But now we know that reflected absolute value, okay, is going to the left. It is about the first region. So the velocity is h bar k over m, b squared, upon incident. It's also in the same region. So the same velocity, but in different direction, a squared. Therefore, you have this. Now, if you remember b over a squared, that's fine, it works, but you may have trouble doing other problems. Secondly, the transmission coefficient. Again, properly, it is the transmitted current density upon the incident current density. Now, you know that the transmission happens in region 3. Okay? Only for this case, the same potential energy, you have this velocity being the same. Otherwise, in region 3, the velocity is different from the incident one in region 1. Okay? This is to say, generally, the prefactor don't cancel out. Okay? Then you have this transmission. This is the last page of today, just to remind you. For a more general problem, don't say this is the transmission coefficient. It's not. The reason is that the definition is about current density ratio, but they are now in different regions. Transmitted is in third, therefore, the velocity is different. It's h bar, the k is different, right? It's k third region divided by m. Incident happens in the first region, is h bar k first region divided by m. Only h bar and m cancels, the k couldn't. This is the proper definition of the transmission coefficient. Okay, so I will stop here today. Next time I remind you of the key feature of the result, and then we will move back to alpha particle decay and other applications of tunneling that developed over the last 90 years. Okay, so I will stop here today. If you have any questions, please ask.